Welcome back to this course on polymer chemistry, and in this lecture we will discuss about polymer additives. We will talk about chemistry of polymer additives and we will give examples of polymer degradation and how the stabilization is done using externally added additives. We will talk about antioxidants and how they function in a polymer matrix. We will talk about light stabilizer and then flame retardants. Now, let us first understand why we need to add additives in polymers. Why should we care at all? Now, if you look at the production of thermoplastics alone, there are over 120 million metric tons. Now, out of this entire volume, 95% and more would have been useless without stabilization by adding external additives. For example, these pure polyolefins like polyethylenes, polypropylenes, they oxidize very rapidly. So, basically drying them is very difficult unless they are stabilized by adding external additives. Pure PVC cannot be extruded and molded at a higher temperature, their processing temperature without degradation. So, if we do not add additives for stabilization, then the polyvinyl chloride we get out of the molded part will have very poor mechanical properties which are not useful for particular application. So, we require stabilization to have these polymers applicable in the applications where they are currently used. So, the successful application of polymeric materials is substantially attributable to the incorporation of the additives into the virgin resin we just produce from the reactor. Unless if we do not use the additives in those resins which are coming out of the reactor, their applicability will come down drastically. What does additives do? Additives enable the polymers to overcome the processing difficulties. For example, the polyvinyl chloride we just mentioned. It also help in overcoming some performance limitations, and it also give the protection in the polymer from the environment. We discussed about the weathering condition, weatherability, where polymer is experience UV light and other parameters. So, if we stabilize the polymer keeping those applications in mind, then the applicability will go up. So, basically by using additives we can enhance or we can overcome the limited environmental stability of the polymers. Now, how do you choose polymers? Which additives for a particular polymers? Now, the nature of the additives we must use or we use must be dependent on several parameters. For example, composition of the polymer. The additives must be chosen keeping in mind the chemical composition of polymer. The additive must be compatible in the sense that it should not react with the polymer itself, or it should not make any harm to the polymer itself, which will deteriorate the polymer property. Processing condition. Now, we must know the processing condition of the polymer for which we want to use the additive. Now, that will that will give the temperature of use and the amount of shear. So, the additives which we are using or you plan to use must survive those conditions themselves. So, if you use some additives which do not survive the condition of the processing of the polymer which you are interested, then obviously the additives will not function after the molded part or the final part is made. And obviously, and also the interaction between the additives and polymer might be different at that higher condition, higher temperature and higher shear rate. So, those things has to be kept in mind. Obviously, the target application has to be kept in mind, which for which application you want to use that additive. And we must remember, if you are talking about the stabilization specifically, we must remember the mechanism by which the polymers are degraded when subject to heat, light, shear, moisture, either during the processing or during the manufacture and during its life cycle. So, basically if you want to stabilize or if you want to have a polymer made with the help of with addition of additives, and we must know the mechanism by which the properties of the polymer deteriorates with or in presence of light, heat, shear during the processing or during the use of the polymers in actual application. Normal chain good polymers like polyolefins or polystyrene, polyvinyl chloride, they have this carbon hydrogen bond, carbon chlorine bonds. These bonds are very prone to degradation by a variety of environmental agents. So, these are the polymer generally require protection against oxidation, light and protection against UV light and thermal degradation, etc. So, this is example about the chemical structure. We need to keep in mind the chemical structure of the polymers when you design a additive. Step growth polymers generally do not have these bonds which are very prone for degradation, but they do have the functional groups which are prone to hydrolysis, like these ester groups, amide groups or carbonate groups. These groups typically hydrolyze very easily, and especially in presence of impurities, metal impurities and acids and bases. So, these polymers actually undergo molecular degradation in presence of moisture, and this hydrolysis, such hydrolysis is favored during high temperature processing, and these are accelerated by this hydrolysis is accelerated by the presence of residual catalyst. So, you must have this keep in mind when you design additives for step growth polymers. Additives are also added to impart new and enhanced properties like in the polymer, like fire resistance, static dissipation, improvement in mechanical properties, to compatibilize the blends and so on. So, there are many more examples where the property of the polymers are enhanced by use of adding external additives. And typically in a polymer formulation more than one additives are used, and so a understanding of the mutual interaction between these additives are essential for making optimal formulations. And generally these small organic additives, they work by sacrificial mechanism. By term sacrificial mechanism meaning that they do destroy themselves and protect the polymer, the main polymer which you want to maintain or retain. So, basically they destroy themselves by doing some chemical reaction and sacrifice themselves to protect the main polymer in concern. So, we can classify the polymers in several ways, and we can for example, we can classify them as protective additives, which they are the additives which prevent or delay or influence the aging process or degradation process of the polymers. And some of the additives used are antioxidants, which basically prevent against oxidation, heat stabilizer, which prevents degradation of polymer under heat, light stabilizer, which basically protect the polymer from UV radiation, antimicrobials, which protect polymer from microbes, bacteria and so on, metal deactivators, which basically deactivate the catalyst residues or metallic impurities residues, which basically help or which basically degrades the polymer during its use or in processing time. Structure modifier, the additives which modify or influence the molecular or supramolecular structures, like compatibilizer, they help in making compatibilized blend. Cross linking agents, which obviously introduce or added to bring cross linking between polymer chains. Nucleating agents, they basically added to increase the crystallinity. Dispersing agents, which are used for dispersing some fillers in the polymer matrix. Foaming, defoaming agents, which are added to make foamed polymer product. There are additives which are used in polymer formulations, which basically assist in processing and fabrication or in assembly, like lubricants, mold release agents, which basically help in releasing the mold from after the part is formed. Processing aid, addition promoters, scavenger, acid neutralizer, catalyst quenchers. There are some other generic examples of this type of additives. As I said earlier, that there are numerous additives are added to increase the property or enhance the properties of polymers, and there could be list of many such additives. For example, flame retardants, which help in reducing the flammability of the polymers. Impact modifier, anti-static agents, anti-blocking agents, anti-fogging agents, optical brighteners, pigment colorants, coupling agent, plasticizers, reinforcement. So many things can be added to enhance the property, and obviously you cannot add all this for every polymer, and it depends upon the final applications. If your application require a polymers which is flame resistant, then you must add a flame retardant to it. And if you are making a polymers which will be like a packaging film for food wrapping application, then if it is having anti-fogging additives, then it will prevent fogging or condensation of the water moisture in the packaging film, which will basically allow the customers to look through that film. If the anti-fogging agents or additives were not present, it will condense and the customers would not be able to look through that film. So, that will basically be a bad property of that film. Now, Before we discuss in the chemistry, there are some issues about the additives we must consider is how do they function, the mechanism. Obviously, chemistry plays a major role in this, and cost. Though an amount of additives are added in small quantity, but typically they are much costlier than the base resin. So, basically one must remember or must consider the cost of the additives used. Even though the amount of the additives used are less, but because of their higher cost compared to the base resin, the cost of the polymer formulation would be higher. So, the cost for the particular application must be kept in mind of the manufacturer. Proper amount of loading, sometimes these additives function for a particular level of loading. Too less loading or might not be bring about the advantage which are the manufacturer are looking for, and too much of addition of the additive might destroy the polymer itself. Obviously, the cost of the formulation will go up. So, the optimum loading of the additives is what required, and we must know the interaction of the additives with the plastics. What is the how they interact with plastics, interaction with other additives, as we said, then multiple additives are used same time. So, interaction with other additives are also be important, and long term issues like how they function, their long term longevity and their effect in the environment, this should be considered. For example, if you are using some that packaging film for food application, then the additive should not leak out and contaminate the food. For example, if you are adding some additives for some medical application, then the additive should not come out and contaminate the medical devices. So, that should be considered before the polymer is used. How it is handling of the additives also concerned. For example, liquid additives are normally difficult to handle. If you are using a polymer powder and if you want to add liquid, the dispersion of the additives in the polymer powder is difficult. So, how you must know how you will handle the additives which you are going to add in the formulation, and how you are going to mixing with the plastics, that is important. Let us take an example about polymer degradation. We are discussing that polymer might degrade in presence of UV light or in presence of heat or light. Now, let us talk about one of the common example of polymer degradation and stabilization, and let us example of polyvinyl chloride degradation. Now, this is, as you know, this is the structure of polyvinyl chloride, but along with the main chain there could be some other units in the polymer backbone. The number is very less, it is given 4 to 6 out of 1000 repeat units, 0.2 to 1.6 out of 1000 repeat units. So, basically these irregularities are very less in the polymer chain, but the degradation is mainly caused by these irregularities itself, not the main polymer chain. So, the unsaturation and the tertiary chlorines are very bad for thermal stability for polyvinyl chloride, and this unsaturation or the presence of terminal chlorine arises due to the chain transfer reaction during polymerization, and it is very difficult to avoid those reactions, and these sites serve as chlorine radical source which basically initiate the degradation. So, the main degradation happen by dehydrochloration as shown in these figures. The main degradation of polyvinyl chloride happen due to the dehydrochloration at higher temperature, and that starts with chlorine radical. And if you have this conjugation over 5 carbon atom or 5 double bonds, basically then it will produce color, and this degradation is accelerated by in presence of light, heat, oxygen and presence of acids, and color may form also from the protonated polyenes as it is shown in this figure. So, basically if you want to stabilize polyvinyl chloride, you basically want to have a mechanism by which you can trap chloride chlorine radical, or you can destroy this olefinic or allylic double bonds which is getting produced during the degradation process. So, how the stabilization is done? One example, there are many additives can be used. One type of additives are shown here. They convert this unstable allyl chlorides to non-allyl sites, and example be dibutyl tin disulfides, and their chemical reaction with the allylic double bond is shown here. So, they form this allyl chloride to non-allyl sites and prevent degradation. And there are additives like dibutyl tin malate which basically break up the conjugated double bond and prevent the degradation further. There are other additives used for PVC stabilizations like soaps of cadmium, zinc, barium salts, and they act as a acid scavenger. Lead salts also act as acid scavenger, and they basically are one of the major additives used in PVC industry. So, this is one example we just discussed about PVC, and PVC is a very prone to degradation under processing. So, this is one example, is a very good example to discuss about polymer degradation and stabilization. Now, let us talk about one more class of additives, antioxidants. Now, antioxidants basically retard the oxidative degradation process of polymers, which is initiated. The oxidative degradation is initiated when free radicals are created in the polymer material by either heat, UV, mechanical shear or metallic impurities. So, antioxidant basically retard the oxidative degradation process. Now, to know the antioxidant additives which are used, let us discuss the basic auto oxidation scheme for a minute. So, let us go through and look this basic. Now, first step is basically initiation. So, you have a initiator forming a initiator radical which might abstract at hydrogen from polymer backbone, forming a radical in the backbone, Now, this R dot can be produced by the homolytic cleavage of these CH type bonds in presence of heat from the polymer itself. Next, normally the propagation step, where it reacts with oxygen forming peroxy radical, and this radical start the further chain reaction forming further radical. Termination of this chain might happen by reaction between the radicals. Basically, reaction between two radicals. Now, if R has an alpha hydrogen, it can further form a ketonic type moiety. So, this reaction only happens that R has alpha hydrogen. The other secondary and branching reaction can also happen. Secondary and branching reactions. Hydroperoxide can give other radical. If R is tertiary, if R has alpha hydrogen. So, these are the basic auto oxidation mechanism by which oxidative degradation might happen. It's, as you can see, it's a radical process. Now, to prevent this, so if you want to design antioxidant, you basically have to attack or stop all these processes. Now, antioxidants are added or designed which cannot attack or prevent all these steps, but it might prevent some step in between. So, one thing can be possible if you want to use stop this auto oxidation, you might reduce the concentration of the I radical or the R dot. You can reduce the concentration of I dot or R radical. Now, that is basically out of our hand, because the processing and the other external conditions we cannot control. So, what we can do, we can trap this R dot or say peroxy radical, and that is done by primary antioxidant. So, primary antioxidants basically trap this R dot and peroxy radicals. We can increase the rate of termination reaction and that is done by addition of hindered amines, and we can also do Now, decompose the, for stop this step we can decompose this by non radical pathways, okay. And this is typically done by use of secondary antioxidants. So, basically we know what are the step in oxidation process, auto oxidation processes, normal initiation, propagation, termination, and secondary and branching reactions. And to prevent that, what are the things we might do, or it is typically done? You can always reduce the radical concentration, but it is not in our hand. So, we can add additives which can trap this radical R dot or peroxy radicals, which is done by adding primary antioxidant. We can increase the rate of termination reaction, which is done by adding hindered amine, or we can decompose this hydroperoxides by non-radical pathways, and that is done by adding secondary antioxidant. Example of these primary antioxidants, hindered amines, and secondary antioxidants, and how they do this trapping or decomposition or increase in the rate of termination, I will discuss briefly now. So, primary antioxidant, as I said, as I just mentioned, it traps this R dot and peroxy radicals, and there are several types of primary antioxidants. One is hindered phenols. They basically terminate the peroxy radicals, as I just mentioned, and they themselves are not discoloring, but they can form chromophoric structures after they do this peroxy radical trapping. One example, very common example, is BHT, butyl hydroxytoluene. Structure is shown here. They are used, this type of primary antioxidants are used very much for styrenics, vinylics, and elastomers. But the drawback for these primary antioxidants that they form very volatile and low molecular weight phenolics. So, they might get lost during the processing conditions. So, these are the mechanism by which they work. For example, this additive trap this radical, form a radical themselves, which can rearrange and react with the other radicals and form non-radical species, and this final species like stilbenequinone or benzoquinone, they basically are sometimes color bodies. So, these additives themselves is not or they do not decolor the polymer, but final compounds when they form after stabilization, that could generate color in the polymer matrix. So, that is the one drawback, and each radical basically capture 2-3 radicals, and by which they basically prevent this oxidation process. Some other mechanism continuing from the last page, how this type of butyl hydroxytoluenes capture or trap the radicals are shown here. So, basically they capture or trap the radical produced, and by doing this they basically reduce the oxidation process, and the only drawback is that they sometimes form a colored compound in doing that. These are some examples. There are many phenolic antioxidants available in the market. These are some example shown here. They are these phenolic antioxidants. And one thing it can be noted, not only for this antioxidant, for all other additives as well, that it's not always that all these additives will work for a particular polymer or all polymers. So, basically there are some trial and error experiments one need to do to find out the best possible additives for the polymer you are looking for. So, there some experiments must be done looking at the mechanism by which the stabilization or the additives, what function you are adding the additives for, that is done. The aromatic amine antioxidants, hindered amines, which basically as we said, they increase the rate of termination reactions. So, they are amines, secondary allyl amines, function by hydrogen donation, and they act as chain terminators or peroxide decomposers. The drawback is that they might produce color bodies, and that will discolor the polymer matrix. Now, these are the some examples I am keeping on. There could be many more examples of these type of additives, but this is just for your knowledge that these are the possible way of using additives and how they actually do their job. For example, primary antioxidants by trapping the radicals, and this by increasing the termination reaction. Secondary antioxidants, the hydroperoxide decomposers react with hydroperoxides and produce non-radical products, and examples are like divalent phosphorus, divalent sulfur compound containing compounds, phosphites, thioesters. These are the common examples of secondary antioxidants. For example, how they work, phosphites, they basically decompose these hydroperoxides and form non-radical products, and thereby decrease the concentration of hydroperoxide, hence decrease the auto oxidation process. Some commercial phosphite antioxidants are shown here. Again, there are many more, and there is no bias for these antioxidants from my point. These are just examples arbitrarily chosen from the literature. Now, we mentioned or I mentioned that the strip growth polymers have those functional groups like esters, carbonates or amides. They are prone to hydrolyze. For example, this PET is shown here, polyethylene terephthalate polyester. They can react with water and hydrolyze, and hydrolysis process basically reduce the chain length, and when the chain length is reduced, molecular weight goes down and the properties of the polymer also goes down. And this happens as I mentioned, this for linear polyesters, polyamides, polyurethanes, polyureas, polycarbonates, where there are functional groups which are prone to hydrolyze, and they are catalyzed by presence of acids or bases. We know from our knowledge of organic chemistry that hydrolysis is catalyzed by the presence of acid and bases, and vinyl polymers do not usually undergo this type of hydrolysis, and This is one example of the hydrolysis happening during the processing condition at higher temperature at higher shear rate. This is for a polyethylene terephthalate which has been dried for 100 degrees centigrade at 24 hours. That means the moisture content in this polyethylene terephthalate sample is very less. So, during processing the hydrolysis is less. So, the molecular drop, hence the viscosity drop is less, whereas if we take a undried PET which have significant amount of moisture in the sample, then it actually hydrolyzes very soon in that high temperature and high shear condition during processing. As a result, molecular weight drops and viscosity of the sample also drops. Let us talk about next light stabilizer. Light stabilizers are added as additive to eliminate or reduce the reactions in the polymers caused by visible or UV light radiation. Now, most engineering plastics or high performance plastics or polymers, they contain aromatic groups which intensely absorb UV light around 290 nanometer, and this is most susceptible light in this wavelength, which corresponds to 95 kilocalorie per Einstein energy, and that can break most of the chemical bonds. So, basically absorption of UV light is basically a deterrent for the polymer molecules, and once the bond cleavage starts, you can get lots of chemical bodies forming which absorb the UV visible, near UV visible range, forming yellow color of the polymer. So, you can use two or three types of UV stabilizers. One, UV absorbers, which basically absorb and effectively skin the UV light from interacting with bulk of the polymer matrices. Other types of UV stabilizer, hindered amine light stabilizer HALS, which basically arrest the chemical chain reaction resulting from the free radical, which basically are free radicals scavengers, and these two can be added together sometimes to have a synergistic benefit for engineering plastics. Let us take example of photodegradation of one polymer. In this case, let us talk about polystyrene. So, with the exposure to UV light, it turns yellow as a result of that bond cleavage by high energy UV light, and as a result the polymer becomes embrittle, and this degradation of molecular weight happens faster in outdoor conditions because it gets exposed to the UV light much more extent than indoor conditions. In case of polystyrene, as we said, that with presence of aromatic groups which basically responsible for absorption of UV light, and that actually causes ring oxidation, and which can basically initiate the polymer degradation process as shown in this figure, and finally they can form this chromophores which is responsible for the yellowing of the polymer material. Another example, photodegradation of polycarbonate. If you take BPA polycarbonate and keep it outside for 1 to 1.5 hours, it turns yellow, it becomes hazy and brittle after that time. And there are two pathways by which BPA polycarbonate, bisphenol A polycarbonate undergo photooxidation. These two path is shown here. There could be rearrangement, molecular rearrangement due to absorption of UV light, or it could be, in this case it could be due to photooxidation product, and this basically produced highly colored product. So, the polymer matrix becomes yellow, and this process also the polymer property, a polymer molecular drops and the property of the polymers become significantly lower compared to what it was originally after the molding. So, light stabilizer must basically we talked about two types of light stabilizer, one which can absorb the UV light and protect the bulk of the polymer from UV light, and second we talked about HALS, which basically prevent the oxidation process or the radical process and prevent the molecular degradation. These are some example of organic light stabilizers. Again, there are many stabilizers available in the market. I just took few examples, and their UV visible spectra is shown. As you can see from the absorbance, they actually absorb heavily in the UV range, and because they absorb, they actually prevent the bulk of the polymer from getting exposed to the UV condition. Now, their mechanism of this absorption, UV absorption happens that they basically absorb, and then at excited state protons transfer happen, and finally they form a new excited state, from which they, by a radiation less process, they come back to the new ground state. So, this is example of that photostabilizer in normal ground state, and with absorption of UV light they go to a first excited state where a proton transfer happen, and finally a radiation less process bring them back to a new ground state. So, by this mechanism, this is the mechanism by which these organic light stabilizers function as a photostabilizer. There could be inorganic light stabilizer or photostabilizer as well. For example, carbon blacks, and they have particle size from 20 to 40 nanometers, and they are very effective absorber, but obviously they can be all be used in samples which are meant to be black. Titanium oxide is another UV absorber which absorbs highly below 370 nanometer. Another example could be zinc oxide and iron oxide, but some other pigments also can be used, but these are not these inorganic light stabilizer, though they protect from UV light, but they have some other problems which basically prevent their use in practical applications. So, these are the inorganic light stabilizer, they do not get used very frequently in applications, in real applications. The other stabilizers like hindered amine light stabilizers we just talk about, which basically prevent the radical process. So, basically trap the radicals and form non-radical process, and by which they prevent degradation of molecular weight and formation of yellow color bodies. And some of the commercially available hindered amide light stabilizers are shown here. These are the again representative examples of some light stabilizers commonly used in polymers. Now, what we will do, I will let us stop for this lecture at this moment, and what we will do, I will in the next lecture, which will go in the last lecture of this course, we will talk about the other types of additives like this fire retardants, how they work, what is their mechanism, and surface migrating additives, and we will talk about polymer blends little bit briefly, and then go to the concluding remarks for the course. So, let us stop here for this lecture, and we will complete the course in next lecture.